Welcome everyone to session a hands-on introduction to bidirectional type interface with Helm by Lucas Dutton and Christopher Anand. Without further delay, over to you, Lucas.
Thank you. So, welcome everyone to a hands-on introduction to bidirectional type inference with Elm. My name is Lucas, and my other co-presenter here is Christopher Anand, but I'll be doing most of the presentation here. So, more about me. Again, my name is Lucas. I'm a PhD student in computer science at McMaster University in Canada. My interests are in functional programming and type theory. So let's jump right into the motivation for bidirectional type inference. So most modern languages have types attached to the values in the program. So we are familiar with booleans, ints, and there are also a list of integers. So these are types that we give values in our code. And what we do with these types is that we can have a type checker which takes these type annotations. And what it does is it checks that the types are sound in our program. Now, type inference takes it another step further. And what type inference does is that we don't need to annotate our program with types. The type inferencer can guess the types for us. So let's look at an example. This is an example at our program, and let's see if the types in this program make any sense. So this is a function that checks if a number is positive. So we check that for an input x, if it's greater than 0, then we return true. Otherwise, we should return false here. But here we could 0 here, which is wrong. But let's see what the Elm type checker tells us. So if I were to run this, what it says is that the second branch of our if statement here doesn't match all our previous branches. And it says that the number is, well, it is a number, but it's expecting a boolean. And the nice thing about this example is that we didn't annotate this program with any types. So the Elm type checker is actually performing type inferencing. So let's talk about why we want bidirectional type inference. Again, our example above only uses type inference, and it uses a specific form of type inference called Hindley-Muir type inference. What this algorithm does is that if we don't know the type completely, what it does is that it creates variables to represent these unknown types when it performs the type inferencing algorithm. And what you will end up with is you will have a list of unknown types, and you want to check that these unknown types will eventually resolve to a concrete type. So it uses this process called unification to solve this series of type equations once it performs this type inference process. The key thing about this algorithm that it doesn't do everything in one pass. So it first does type inferencing, then it does unification. And the downside to that is that the type error messages will get complicated. And the algorithm itself isn't easy to understand. So why we will talk about bidirectional type inference in this presentation is because it just uses a one-pass method and is implemented with two mutually recursive functions, check and infer. This simple structure means that a user needs to provide more type annotations. So for example, top-level functions usually require type annotations for this algorithm to work. So while it requires more user input, the error messages will be better localized and more understandable. So here's a roadmap to implement bidirectional type inference. So first, we will define a simple language, and we will define types for our language. And then we will define what we call typing judgments which allows us to define what the algorithm does to check the types in our language. So we will use the Elm programming language to implement our simple language above. And we will be providing links to an online Elm IDE on this website, stable.rocks. In this fork link, we will give a code skeleton of the implementation. And we will do a live demo of implementing this type inferencing algorithm. And most of the test cases and code parsing will be provided in the code. So later when I start to present this type inferencing algorithm, my co-presenter will share links to this online IDE so that you can follow along the code implementation. Okay, let's first talk about our simple language that we are going to define here. So we are defining what is called the simply typed lambda calculus, and it only has 3 constructs. So it has variables, it has function declarations, and it has a way to apply these functions called function application. So the presentation will only focus on these 3 parts, but we can also extend this language to have some of the features that we see in most programming languages that we are using nowadays. So there are if then else expressions. We will use the booleans and integers as constants in our programming language. We will have binary operations, predicates, and very importantly, we need type annotations for our language. So this is some example code that we could write in our simple language. So we can write this if then else statement, and we can annotate it to be an integer type because the branches here return integers. So this should be annotated as an integer. We can have Boolean expressions as well with an annotation here. We can have lambdas, and the syntax looks like what you would see in Elm or Haskell. So it starts with this slash, a variable name, an arrow, and then the body of our function. And we can have function application, which is just applying a function followed by a white space followed by the value that we are applying the function to. So we need what we call an abstract syntax tree representation of our language. And the way we do this in Elm is to use an algebraic data type. So here we have our algebraic data type expression. We have variables, a function declaration, which takes a string as our input variable. So this will be the name of our variable and the body of our function declaration, which is just an expression. So this type will be recursive. We have function applications, so applying an expression to another expression. And we can annotate any expression with its type. So these constructors here are not covered in the presentation here, but it will be in the provided code. Then we need another algebraic data type for types in our simple language. So we have 2 base types, which are integers and booleans. And we have a way to create functions. So this is a function type, which is an arrow from a type to another type. So this will be our input, and this will be our output. So using our algebraic data types above, we can represent our programs with those constructors that we define. So for example, if we want to define an if then else, we can define it with first an annotation that it is an integer type. And then we use the if constructor. And to represent 5 is lesser than -10, we can use this pred-op constructor with the less than comparison operator. And our 2 integer types are wrapped with the integer constructor. And the 2 branches are integer 2 and integer 1. So it's similar with this Boolean expression and function expression here. But let's keep going here. So one other Elm prerequisite we need to implement this language is that we need to store the type of our variables inside some context, which we call this gamma symbol here, while we are running our algorithm. So we want a mapping from a variable name to its type. And to do that, we need a dictionary data structure. And we will just use Elm's dictionary, which is provided in the standard library. So we will use two operations. We will need to be able to get the type of a variable. So get just receives the key, and it gets the value associated to that key. And we need to be able to insert a variable with its corresponding type, and that's with this dict.insert function. And this is the link to the dictionary type. Okay, so let's talk about the type judgments of our language. So this uses a mathematical representation here, which it's more commonly known as deduction rules. But when we are using these deduction rules to talk about types, we call them type judgments. So there are three parts to a type judgment. The first part is what we call a premise. So a premise is something or a condition that needs to be satisfied before we can get a conclusion of our type judgment. Now, in this case, the premise says that some variable x needs to be of some type tau, and this needs to be inside our context gal. And if this premise is satisfied, then we can acquire a conclusion. The conclusion here says that from gamma, we deduce, and the deduction symbol here is this tilted T, which most people call turnstile. And after this turnstile symbol, it tells us what we can deduce from our context. And here we deduce that x is of type tau. So this rule is very simple because the premise and the conclusion are almost identical. This just says that if we can look up a variable with a type inside a context, then we can immediately conclude that the variable has that corresponding type. And the name of this type judgment is labeled as T-bot. Now, it's harder to understand this without looking at some concrete code. So below here is an example Elm implementation that implements this type judgment. So this is where we need our dictionary data structure. And we can use a type alias to define what our context will be. So our context is defined as a dictionary mapping variable names, which are strings, to their corresponding type. And here we have our type inference function, which takes in two inputs. It takes our current context and the expression that we want to infer our type. And it returns this maybe type. So the reason why it's a maybe is because sometimes our type inferencing algorithm will fail. For example, if our program doesn't have the right types, then we need to inform our user that the types in their program is wrong. And so this is what the maybe is for. It is to represent failure in our algorithm. So to perform a type inference on this variable here, we need to do a case expression on the expression that we want to perform type inference on. And one of the cases here we are interested in is the variable. And following this type judgment, now the way we read our type judgment here previously was reading the premise and then reading the conclusion. But what the implementation here does is that it starts from the conclusion and it goes into the premise. Now, why do I say that? Is because this context and expression is given in the conclusion here with this gamma and this x. And what we are doing here essentially is we are taking X and looking it up in gamma. And that's what the premise does here. And to do that lookup, we use the get function of our variable X, and our dictionary is the context in this case. So moving on to another example. So when we want to do type inference on function application, what we will need if we start from the conclusion is we need our function application to be two expressions, expression E1 applied to expression E2. And the result of this function application needs to be of type tau2. Now, to be able to get this, we first need E1 to be a function type, which means it needs to be of type tau1 goes to tau2. And since we're applying E1 to E2, that means E2 needs to have type tau1 to match the input type of our function. So if we look at the code, we start with our expression, the one app E1, E2, and from there we can perform recursive type inference on the function expression, which is E1, and what the function is being applied to, which is E2. And since this is recursively calling infer type, it's going to return a maybe type. The maybe type will be either just or nothing. We know that if it's nothing for either two cases, it means that our type inferencing has failed. If it is just for both, what you will see here in the first case, which is for E1, we need a function type for E1. It cannot be a primitive type. So that's why we need to match on this function type here. And we call it T1 and T2. And our E2 will be T11. And we need to perform one extra check here before we declare this a success. So we need the type T11 to match the input type of our function T1. Now, in our inference rule, we did not need to perform this equality comparison because this tau1 here are symbolically the same variables. But in our code, these are not the same two variables, so we need to perform this equality check here. So if that works, then we just return T2. Otherwise, we do not need to return a success, we return nothing. Now, we run into a problem with function declarations. And the reason for that is, if we again look at the type judgment here, we start with our function application with a type T1 to tau2. And what you will see is we need to insert the type of X into our context. So we start with our context, and this comma here represents an extension to our context. And we are extending it with the type of X, which has to be tau1. And from here, we will recursively call the infer type and infer our body to be of type tau2. So the problem here is that we do not know at this point in time the type of X. So we will need to guess the type of X before we insert it into the dictionary. So if this was using Hindley-Muir type inference, we would be able to use unification to guess a type for X. Otherwise, we will need to invent a type for this tau1 here. Okay, so this is where bidirectional type checking comes into the picture. So previously, we were running everything inside an inference function. But what we will do now is we will split the type judgment into two separate functions. So we will still have our inference function, and it takes our context and our expression as input, and it would output the type of that expression. But now we have a new function, which is our check function, which actually takes our type as input instead of returning it as output. So I've color-coded our variables here. If it's color-coded blue, it means it's going to be input. And if it's color-coded orange, it will be output. So for each of the type judgments we just saw, we can now choose to either keep running it in inference mode, or we can run it in our check mode. And the key difference between these two functions is that our check function now takes the type annotation of our expression, and it still returns a maybe type here, but the type that it returns here would be equal to the type that we are supplying here. Okay, I don't know if the logins are already shared, but now would be a good time to share the logins because we will start implementing our bidirectional type inference algorithm.
Okay, everybody has a login, and I'm going to share the fork link. So you have to log in first. Once you've logged in, then you will be able to create a fork of the code that Lucas is showing. I think you can keep going, Lucas.
Yep. Okay. So if I open the fork link, which is in my other tab here, you can see that we have our info type function and we have our check type function. If we look at the right here, we have a text box to input some test cases. And we have our type checking result. So right now, it's most of what we are going to do has still need to be implemented. So the type checking result is returning nothing. But what we would see is as we implement more of the features, this would actually return a type checking result. And this table is some unit tests. Right now, only 2 of the test cases work. We have this integer, which is returning an integer type as the type checking result, but most of these still don't work. So let's get into implementing the check type and info type cases here. So where we left off in the presentation is that we need to introduce 2 new extra rules in our bidirectional checking algorithm. So the first rule we need is a way to switch from checking mode to infer mode. And what this means is that anytime that we can check a function, we can also infer, every time we need to check an expression, we can also infer that expression. So it's a catch-all case in the implementation. So let's go to the case check infer here. So right now it's left as a to-do, and we are going to fill this with the actual implementation. So we want to switch from a check to an infer, and we have our inputs, context, expression, and type. So we want to infer our expression with our context. And the infer mode is a maybe type, so it would either retain a just with a type, and we would do something here, but if it returns a nothing, it means that we should also return a nothing. Now, if it returns a type, which I've labeled type 1, this type should match the input type of check type. So we will need to do an equality check here. So we say if the types are equal, then we can return. It doesn't matter which one we return, we just need to return one of them. Otherwise, if they're not equal, it means that something has gone wrong. So we return nothing. Okay, so that's for check infer. Another rule we will need is for type annotations. So annotations inside of check can be swapped to infer mode because we can use the annotation to check the type. sorry, if they are running infer, that means we can run it in check. So this will be done inside infer type. Okay, so this is the annotation case here. So let's implement this. So when annotation is matching infer type, we will check its type. And we have the pieces we need, which is context. The expression would be this E here. And since check type requires an additional type argument, we just take the annotation type as the input. Okay, so those are the two additional rules we need. Let's look back at the three cases, which are variables, function application, and function declaration. So variables can still be kept inside of infer type, and it does the exact same thing. So we are still returning our type here as an output, but we have all we need to be able to infer this type by looking it up in the context. So we are going back to infer type in our code, and we are going to use the get function as our implementation. So we want to get the type of X, which is our variable name, inside our context. Okay, and you will see now that this test case should now be showing a just integer type, where previously it was showing nothing. So let's go into function application now. So function application is still run inside of infer type. So for function application, what you will notice in the type judgment rule is we will run E1 inside of infer mode, but for E2, instead of inferring the type of E2, we are going to check the type of E2. The reason for this is when we infer the type of E1, we will get access to T1 and T2. And since we have access to T1, we can then use T1 as the checking input to E2. So let's implement function application. So first, we want to infer the type of the function expression. So we still give it the context and P1. And we know that if it's nothing, then we'll return nothing. Actually, we'll use a catch-all case here. And the reason for that is we are only interested in one special case here. And that is if the inference of E1 returns a function type, which should be from T1 arrow to T2. So once we get the type of E1 from type inferencing, then we can check that E2 has type T1. And again, this would be a just or nothing. So if it's just, now we are not interested really in this type here, because we know that this would be equal to T1. And if the check works here, then we can just return the type of our function, which is T2, or the type of our function application. Otherwise, we just return another. Oh. Okay. Right, this should be a just. Okay, so this is good. Now for the last one, which is function declaration. So this is run entirely inside of check. So what we would do is, if we have a function declaration with the variable and the body, what we already have is the type of this function declaration. So we can check that this has to be first a function type. And once we know it's a function type, then we can insert the type of our input X into the dictionary or into the context, and then check the type of our body, which is with its type T2. So let's implement this. So we have to go inside the check type function, and let's implement it here. So first we need to check that this type here for function declaration, it has to be a function arrow. And once we check that it's a function arrow, then we want to insert the type of X into our context. And we are going to use check type recursively. So that inserts the type of X into our context. And we want to check the type of our body E here, and it needs to be of type T2. So here, we don't really care about the type of the result of our check here, because we know that if checking works here, then we can return our type here, which is the type of our function. And otherwise, if it's in nothing, then we return a nothing as well. And we need, so here, if we don't match that our function type is a function arrow, then we should also return a nothing. And if we look at the right-hand side, especially at the unit test now, you will see that the expected and actual types should just match. And if you want, you can run custom test cases here. So this takes input that's similar to Elm or Haskell style code, and it would run a parsing function, and it will give you the type checking result. In this case, we have the identity function, which is it takes an integer and just returns that integer. So it just has the function type integer to integer. Okay, one final point of discussion is, when do we want to infer and when do we want to check for each piece of our syntax in our language? So remember that we ran function application inside of infer, and we ran function declaration inside of check. Now, for function application, the conclusion only has T2 that we want to infer, but we can't really invent a new type for E1. So to be able to acquire information about E1, we would need to run type inference. And it gives us all the required information, which is T1 and T2, which allows us to check the type of E2 and allows us to return the type of our function application. For checking, we need to run in check mode, because remember, before we introduced bidirectional type inferencing, we had to guess a type for our input X. So our way around that is to demand that we need to provide types for our function declarations. So this relies on top-level type annotations for function declarations. And if our function is nested, then their type should already be in the context. Otherwise, the type inferencing algorithm will not succeed. So that's a general rule of thumb on when do you check or when do you infer. You can always check, provided that type annotations are given, but you can't always infer functions. So checking puts the burden of annotation to the user, while inferencing puts the burden on the algorithm to figure out the types. And one other rule of thumb is that we can check constructors and we can infer deconstructors. So we can think of function declarations as a way to construct function types. And since it's considered a constructor, we will check function declarations. Function applications are another way to deconstruct functions. And for those, we can use the inferencing mode of our algorithm. Okay, so to conclude, we can first talk about more features we can add in our language. So we haven't talked about let-in expressions, which a lot of functional languages have as a feature. We haven't really talked about how to implement recursion. Algebraic data types and tuples are also something to implement. And our language only has Booleans and integers, but ideally we would want to support polymorphism. Another thing that we can improve on in our implementation is to give better error messages. Right now, we are only using the maybe type, which returns a nothing if our algorithm fails, but it doesn't tell us why our algorithm failed. So we would need to use the result or the either type to attach error messages to our implementation. And these are two resources on bidirectional type checking, and they are meant to be beginner friendly. So if you understood all that has been covered in this presentation, then you would find that you have no problem following the talk and the tutorial by David Christensen here. And that is the conclusion of the presentation. Thank you for your time and listening. So our foundation, which is the Stable Foundation, is looking for volunteers, and we teach coding to grade school kids. We are looking to expand our program to various languages this year, and we need translations of other languages in our Shape Creator app. So if I open this link, we have this Shape Creator app that allows us to draw shapes using this interface here, and it will generate our code. So right now it's in English, but we have other languages here. And we are looking for translations of even more languages that are not already available here. Okay, thank you again. And I think now is a good time to take questions.
So Lucas and Christopher, I don't think anyone has any questions, so we can end the session. So thanks again for sharing your experience with us, Lucas and Christopher.
Thank you.
Thank you.